Next, we want to talk about comparing cardinalities. So we know that two sets have the same cardinality when there is a bijection, F from A to B. So when do two sets have one that has strictly less cardinality than the other, right? So this should mean they don't have equal cardinality. And if I think about it in terms of finite sets, again, I want to think about what I can say about these sets, but without referring to the number of elements in them. But we saw when we were talking about functions that if we have less elements in A than we do in B, then we can have that injection. It's just not going to be a surjection. It's not going to be onto, because I won't be able to hit everything in B, because B has more elements. So I'm going to say that the cardinality of A is strictly less than the cardinality of B if there is an injective function from A to B, but no bijection. So if I can find an injection but no bijection, then I'll say that the cardinality of A is strictly less than the cardinality of B. So we'll see that more on the next slide. So just to tie up our definitions here. So we say that the cardinalities are equal when there's a bijection. We say that the cardinality of A is strictly less than the cardinality of B when there's an injection but not a bijection. And we say that the cardinality of A is less than or equal to the cardinality of B if I know there is an injection, but I'm just not sure if there is a bijection or not. So we say that less than or equal to. So let's think about the cardinalities we know so far. So the cardinality of N is the same as the cardinality of Q, is the same as the cardinality of Z. And I know that there is no bijection between N and R. And we can pretty easily find an injection, right? I can define a function f from N to R, where f of N is just equal to N. That's going to be an injection, but not a bijection. And I know there is no bijection, so I know that those cardinalities are all strictly less than the cardinality of R. So these are my two different sizes of infinity. And in fact, I can have more sizes of infinity, as we'll see very soon. In particular, we want to ask ourselves, is there anything bigger in terms of cardinalities than R? And in fact, we'll be able to find out that there is, and that's what we'll see the theorem on the next slide is going to allow us to do. So we have this theorem that says if A is any set, then the cardinality of A is always strictly less than the cardinality of its power set. Right, so I know if A is finite, then the cardinality of the power set of A is just equal to 2 to the power of the cardinality of A. So cardinality of A is certainly going to be less than 2 to the power of A for any A. All right, even if I have A equals 0, 2 to the 0 is 1. So that still works. But we have to do this more carefully when we're dealing with infinite sets. So I need to show that there is an injection from A to its power set, but it's completely impossible to find a bijection. So in order to get ready for this proof, we're going to do it together in class, but it's kind of related to the idea of the Barber's paradox that we talked about way back at the beginning of the course. So I want you to review the Barber's paradox. We'll talk about that together as a group in class, and then we will work together to use those ideas to prove this theorem. Now, when we're dealing with these infinities, we often want to think about sets and whether or not they're countably infinite or uncountable. So they have the same cardinality as the natural numbers, or are they bigger, like R is bigger? So we can use these two theorems to help us with that. So if you have an infinite subset of a countably infinite set, it must become countably infinite, right? So if I have my set Z or N here, Let me actually write that. So I have either z or n, it doesn't really matter. And I have a, which is a subset of that, or maybe even it's a subset of the rational numbers. And it's infinite. There's no infinite set that's less than the cardinality. So this is infinite, so it can't be finite. It's a subset of something that's countable, so it must be countable. So that's what my first theorem says. If you're infinite and a subset of the countable set, then you must be countable. And then if you have some uncountable set, right, for example, like R, and something that's bigger than it, or it has that U as its subset, then this also must be uncountable. So you can't have a countable set with an uncountable subset, because that would contradict that first theorem. So these kind of work together. So when I'm thinking about things like the even integers, I can say, oh, well, the even integers are a subset of the integers. It's a finite set that's a subset of a countably infinite set. Therefore, it must be countably infinite. So we can use these to help us determine the size of different sets. Okay, I just want to touch on two things in 14.4. So the main idea of 14.4 is this Cantor-Bernstein-Schroeder theorem. So we're not going to prove that. You're certainly welcome to read through that proof in the book. It's sort of a nice, fun proof. But I do want you to see what this theorem says. So it's, again, dealing with these cardinalities of sets. So it says, if you know that the cardinality of A is less than or equal to the cardinality of B, and the cardinality of B is less than or equal to the cardinality of A, then the cardinality of A equals B, which is good, right? This is the sort of thing that we would hope to be true about this less than or equal to. But because we're dealing with infinities here, it might not be true. So basically it's saying that if we just have these bijections, if you have two injections, so if you have injection one way and an injection the other way, then you have a bijection. So often when we're trying to show that two sets have the same size, instead of coming up with a bijection, I'm just going to think about injections back and forth. And as long as I have those two injections, that's going to imply that I have the same cardinality. So that's going to imply that I have that bijection. So you'll see that being used sometimes, so I wanted to touch on that. And then the last idea I want to touch on is sort of a question here, right? So we know that there is an injection from the natural numbers to the real numbers, just that identity injection. So I do know that I do have this strictly less than. So the question we could ask is there anything in between? So in particular, is there some set A with the cardinality of n strictly less than the cardinality of A, strictly less than the cardinality of R? So is there some set A whose cardinality is strictly between those other two cardinalities? So for a long time, people tried to answer this question to determine whether or not this set A could exist or does exist. And people generally believed that it didn't exist, but they weren't able to prove it. And this sort of gets into these questions about set theory that we talked about again at the beginning of the semester when we were talking about the Barber's paradox and things that you could define and couldn't define. So after a lot of work, and in the 1960s, they were able to deduce that you can't actually prove whether or not this set exists. So it is not possible to determine whether or not this exists. So you can say that it exists as part of your axiom system, and that's totally fine. All of math works. You could also say it doesn't exist, and then everything also works. So it's sort of one of these logical paradoxes. So again, this is called the continuum hypothesis, and I encourage you to read more about that if you're interested.